Very good morning, my dear students. Let's continue. The concept is called moment of inertia. This may be a new terminology for you, but still, it's the most important for any kind of entrance exam. So, the name of the topic is what? Moment of inertia, denoted with the symbol capital I. There are few important things related to the moment of inertia I'll discuss with you right now. Then we will move into the deep analysis of the concept. Number one, moment of inertia is the rotational analog of mass. Mass. Number two, this is depending on mass of the body and, carefully see, mass of the body and distance from the axis of rotation. And number three, the third point, this moment of inertia is a tensor quantity, my dear students. What is that moment of inertia? It's a tensor quantity, my dear students. This is the rotational analog of mass, and this is depending on a mass of the body and the distance from the axis of rotation, and it is a tensor quantity. And let's talk about one by one, and maximum concept of moment of inertia will come here. Number one, it's a rotational analog of mass. Have a look at it. We have already, for example, in linear motion, if I write linear momentum, in rotational motion, we'll write angular momentum. Yes or no? Definitely it says. In translatory motion and linear motion, the terminology, how it will be related, how it will be written in the rotational motion, you already know. For example, a linear velocity. So this will be written as angular velocity in rotatory motion. And for example, the force, which is translational force, or in linear motion, the force acting on a body. So whereas in rotational motion, so this can be written as the torque tau. In the same way, there are so many other quantities what we have written. The linear acceleration A, so that can be written as angular acceleration in rotatory motion alpha. And in the same way, so there is a mass in our linear motion, in angular motion or in rotational motion, the same mass can be represented with a physical quantity called a moment of inertia. So this is the very important. So this is the meaning called rotational analog of mass is the moment of inertia. Rotational analog of mass is the moment of inertia. Understand? Clear? Rotational analog of force is the torque. Rotational analog of linear velocity, it's an angular velocity in that way. Okay? Now, coming back to so many other points. So wherever the mass comes in an equation of linear motion, we can keep moment of inertia. For example, from this only let's discuss. For example, we have the linear momentum is equal to a mass into a velocity, right? So angular momentum we can write from here. What's angular momentum from here, my dear students? So P L, which is equal to mass in linear motion, angular motion or rotational motion, we'll say it's I. V, final velocity, here linear velocity, and this is angular velocity. L is equal to I omega. Understand? Very, very, very important. Now, for example, kinetic energy. Kinetic energy is what? In linear motion, it's half mv square, my dear students. So kinetic energy in rotational motion is equal to half into m. M can be written as I, moment of inertia. V can be written as omega, angular velocity square. This is also an important equation. Understand? Right? And one more for your better understanding. F is equal to ma. Force is equal to mass into acceleration. This force I can write it as torque in rotational motion. This mass I can write it as I, moment of inertia. This acceleration I can write it as alpha, angular acceleration. So tau is equal to I alpha, my dear students, in this way. Right? Clear? F is equal to ma, tau is equal to I alpha. K is E is equal to half mv square. Here Ke in rotational motion half I omega square. Linear momentum is mass into velocity. Here angular momentum is I into omega. So I hope you understand what exactly is the moment of inertia now. At least 50% of the idea you must get from this. What is the moment of inertia? Mass is the measure of inertia there in linear motion, in translation motion. Right? Here, moment of inertia is the measure of inertia in case of rotational motion. Coming back to the second thing. It is depending on mass and the distance. It's depending on what? Mass and the distance. And the second point we'll discuss. This is all related to the first point. And it is so simple to understand the second point, my dear students. So there is a rigid body. Let's take there is a rigid body here. And this is the axis of rotation. The rigid body is connected like this, my dear students. Have a look at it. This is the rigid body is connected like this and rotating. Okay. So about this axis of rotation, this rigid body is rotating. It is so simple, my dear students. See here. So there is a body here, right? Imagine this is the rigid body. So this is my axis of rotation. Simple. So about this axis of rotation, the rigid body is rotating like this. About this axis of rotation, so the rigid body is rotating. Alright? Imagine it is taking a circle like this. So imagine a situation, this is what the rotational, andre a wire or a rod. For this a rigid body is connected like this and this rigid body is rotating. Or in simple ways, a rod, a rigid body is connected and we are just rotating it. So the rigid body is rotating in the circular path about this axis of rotation. Let's take a particle of mass m here. When this rigid body is rotating about this axis of rotation and that particular particle, this is what the rigid body andre ಏನು? In the starting of the class we have discussed, starting of the chapter we have discussed, rigid body is the combination of n number of particles and those particles are called system of particles. So there is m2, there is m3, m4, m5, m6, m7, so on, mn. Here our concentration is about one particular mass small m here and that small m is at a distance r from the axis of rotation and that's called perpendicular distance from the axis of rotation. And concentrate on that particular mass m and how it rotates in the circular path. In this way it is rotating in the circular path. That's it. Like this it is rotating in the circular path. Now let's write the kinetic energy of that particular particle. Kinetic energy is equal to half mv square. The same I can write it in rotational motion. Kinetic energy in rotational motion is half into I into omega square, my dear students. See. Okay. Forget about this. Keep it aside. And from here, we can write kinetic energy in rotational motion half into m into v andre, it's r omega tane. So this v we can write r omega. The relation between linear velocity and angular velocity. So that's a whole square. From here, kinetic energy in rotational motion is equal to half into mr square into omega square. Mr square into omega square. So let's suppose this is equation number 1. And let us take, suppose this is equation number 2. So from 1 and 2 I can compare, because both the expressions are representing the rotational motion only. Kinetic energy in rotational motion, kinetic energy in rotational motion. So let's compare these two, my dear students. On comparing these two equations, what we get it? Half, okay, kinetic energy in rotational motion, which is equal to, right? No, it's not required. See, kinetic energy, rotational motion. Half, omega square, and what is left here? So this is I, right? This is mr square. In the place of I, what is there? In the place of I, what is there? It's mr square. So moment of inertia, I can write it as mr square. This is very important expression. And the SI unit of this moment of inertia is what? SI unit is mass is kilogram and R under meter, it's a meter square. So SI unit of moment of inertia is kg meter square. This is the moment of inertia expression, and coming back to the initial definitions here. So it depends on mass and the distance from the axis of rotation. See here. Moment of inertia is depending on the mass as well as the axis of distance, perpendicular distance from the axis of rotation. So 1, it's finished. 2 is finished. And the third one is a tensor quantity. What is meant by the tensor quantity? And before going to that, we'll do one more thing. So for example, there is another mass, let's take m1. This m1 also is at a perpendicular distance from the axis of rotation, and that m1 also will be moving in the circular path. And for m1 also, if you find in the same way, so moment of inertia you get I1, which is m1 r1 square, and I2, so there is a mass m2, you take it, and for m2 also it is moving in a circular path. Moment of inertia of the second mass, it's m2 r2 square. We are talking about the point masses. As a system we are not talking here, a point mass we are talking. So if you take a mass called m3, that is also moving in a circular path, and for that also I can write moment of inertia of mass m3 about this axis of rotation, m3 r3 square. So ether so on I can write till in. And very important, moment of inertia anta simply we should not say. Moment of inertia of a body or of a mass about which axis of rotation, that is very important. Like in work energy power chapter, my dear students, we have learned. Simply we cannot say work done by what force, that is important. If a body is moving on a surface, on a ground, so for example, a block is dragged on the surface of the earth. So there are so many work done cases are available here. Work done by gravitational force will be there, work done by normal reaction, work done by the friction, work done by the external force. Like this, so many cases of the work done are available. In some cases, work done by the force may be positive. In some cases, it's zero. In some cases, it's negative. In the same way, moment of inertia about which axis of rotation. Here we have specified the axis of rotation. In each and every case, moment of inertia about which axis anta specified ಮಾಡಲೇಬೇಕು. Okay, and related to that specification only, this tensor quantity, you might feel this is completely new. Yes, 100% it's completely new. Right? When you're in the lower classes, imagine a situation when you're learning alphabets, English alphabets, A, B, C, D's. Those are new at that point of time for you. But with the help of teachers, with the help of parents, with the help with the work from your side, you have learned them. The same thing here. Right now, at this situation, so the tensor is a name which is a new alphabet for you. That's it. You decide how much work you do to understand tensor quantity, to understand the moment of inertia, to understand, and this is what the formula I is equal to mr square. Always whatever you have learned in 9th and 10th standard will not repeat here, always. But most of the times it repeats, at least the quantities. Right? So when a new quantity has come in front of you, you take it as a challenge and try to learn it as early as possible. So then only you can spend time on the revision. Alright, so this is what the moment of inertia of an individual masses about this axis of rotation. Once again I am telling you about this axis of rotation. So the moment of inertia of the system, if I want to write, and that will be m1 r1 square plus m2 r2 square plus so on, it goes like that. So, moment of inertia of the system, I can write summation of I is equal to 1 to n mi ri square. So, this is what the moment of inertia of the system expression, my dear students. Moment of inertia of the system expression like this. Moment of inertia of a point mass expression is like this. What is I? Moment of inertia about a particular axis of rotation. What is M? A particular point mass. And what is R? A perpendicular distance between the axis of rotation and that particular mass. That's it. Understand? So let's solve a few numericals related to the moment of inertia and very important areas we are going to cover in today's class. Before moving to that, I have an object here. Why I am continuously specifying axis of rotation, right? Look at here. So, imagine a situation, see? Because this is the axis of rotation, see? Middle angle. This body will have center of mass and this square plate will have center of mass. Square plate. This is the center of mass. And about this center of mass, this will rotate like this. Carefully observe, see? Moment of inertia of this square plate about this axis of rotation we can find. We'll do that. We'll find it. You understand? If you know mass of the square plate and if you know the side length of the square plate, you can find the moment of inertia of this square plate about this axis of rotation. Carefully see. Okay. Now the axis of rotation is at one side of the square plate, my dear students. It's not at the center of mass, you can see. It's not at the center of mass. See? Now, observe carefully. Now, the axis of rotation at one end of the square, one side of the square, not at the center. So, now also the body can rotate like this. Now also the body can rotate like this. Understand? In this case, the moment of inertia of the body is different. Right? For example, the same body can also be rotated like this. Imagine this is the axis of rotation, my dear students. About this axis of rotation also, the body can rotate. Understand? See? So when the axis of rotation is changing, the moment of inertia value will change. When the axis of rotation is passing through the center of mass, right, the value of moment of inertia is different. When the axis of rotation is passing from one end, this is different. Moment of inertia is different. When axis of rotation is like this and the body is rotating, in this case moment of inertia is different, like this. So when the axis of rotation is changing, so the moment of inertia of the body about a particular axis of rotation is changes. So that is the reason the moment of inertia is a tensor quantity. Tensor quantity andre the quantity must keep on changing depends on the axis of rotation. Simple. Okay, and let's continue the concept with some numericals. Okay, fine. Let's take this example. Point masses. This moment of inertia we are going to find for the point masses, then we will be finding for continuous mass distribution. What is meant by the continuous mass distribution? Already we have discussed during the center of mass. If you are not remembering this, anyway I'll introduce once again here, or at least you go back to pages of your notes and go through it. Example. So simple. So there are 2 point masses are kept here, 2 point masses at a distance A. They are connected by a massless rod. Look at here. They are connected by a massless rod of length A between this mass and this mass. Now, the moment of inertia, look at here. This is the center of mass between these two masses. Now the axis of rotation they have considered is this one. Look at this. What is this moment of inertia? That's a question. Imagine a situation. This is what the rod I have. There is mass here and there is a mass here. Observe. There is a mass here and there is a mass here. Now, about the center of mass, this is the axis of rotation. Look at here. Both the masses are rotating like this about this axis of rotation. What is the moment of inertia of the system? So this is the situation. The rod you need to consider as a massless. It's given, it's massless. So the moment of inertia for the point masses concept comes now. What is that? Massless rod. Observe. Moment of inertia of the first body, its mass into square of the perpendicular distance from axis of rotation. Imagine it's my first body and this is the second body, and look at here. So this is what the perpendicular distance between axis and the first body. So that's A by 2 whole square. In the same way, second one. M into moment of inertia of the second body about this axis of rotation. M into, so what is the perpendicular distance from axis of rotation? It's A by 2 whole square. Right? So we need the total moment of inertia of the system. So M A square by 4 plus M A square by 4. Right? So what is this? It's 2ma square by 4, and 2 and 4 if get cancelled in denominator there will be 2ma square by 2. That's it. So this is the final answer for the moment of inertia of the system. Let's look at the next question. Your confidence and the concept will build up right now. Look at here. So there is a triangle which is made due to the massless rods. This is one massless rod, this is another massless, and this is another massless rod. So there is a mass M is kept here, there is a point mass M is kept here, point mass M is kept here. Let's imagine this is number 1 first mass, and this is second mass, this is the third mass. Okay. Observe. Axis of rotation is this. This is the axis of rotation, my dear students. Imagine it is x dash. What is the moment of inertia about x dash? That's a question. Simple. Moment of inertia of, see, what does it mean? You know, about this axis of rotation, this triangle is rotating at the meaning. About this axis of rotation, this triangle is rotating. Simple. This triangular system is rotating. Whenever they are asking about moment of inertia of the system, moment of inertia of the first body about this axis of rotation, moment of inertia of the second body about this axis of rotation, moment of inertia of the third body about this axis of rotation. That is important. Now, this is an equilateral triangle whose side length is A and A side length. This is A andre, so this is A by 2 and this is also A by 2. Alright, A by 2 and A by 2. Okay. Now we are talking about the point masses only. Alright. ಈ ಕೇಸಲ್ಲಿ about x dash axis of rotation, moment of inertia, what is that? Ix dash is equal to I1 plus I2 plus I3. Nodri how simple it is. Ix dash is equal to I1. Moment of inertia of the first mass about this axis of rotation is how much? So first mass m. What is the square of the perpendicular distance from the axis of rotation? Is it A by 2? Students, is it A by 2? Yes. So A by 2 whole square plus moment of inertia of the second mass from the axis of rotation. So now it is also m into A by 2 whole square plus. So the third one is very important. The third one is very important. Why the third one is important? So third mass is kept on the axis of rotation, my dear children. Third mass is kept on the axis of rotation. When the mass is kept on the axis of rotation, the moment of inertia of that mass about that axis of rotation will be 0 because perpendicular distance is not there. Mass is there, m. Moment of inertia in third case, if I want to write mass estimate m, and what is the perpendicular distance of this mass from axis of rotation? 0 tane. So I3 will be 0. Then what is answer? Then what's answer? So Ix dash is equal to, it is similar to this, right? Ma square by 4 plus Ma square by 4. Ma square by 4 plus Ma square by 4. The answer is Ma square by 2. So it's the final answer. This is the moment of inertia of the system of point masses. 2 point masses, 3 point masses, and you can also make it 4 point masses which are kept at the corners of a square, and you can find the moment of inertia of the system about any axis of rotation. Okay, so now the homework is, listen my dear students, right now you should pause the video and solve this. Right now you should pause the video and solve this and carefully observe my dear children. Here let's take, this is the axis of rotation here. So this is the axis of rotation here. So this is the axis of rotation. Imagine it's a y dash. What is the moment of inertia about an axis y dash? Right now you should solve and tell me. Now this is the axis of rotation. So the complete triangle is rotating like this about this axis of rotation. Alright, moment of inertia of the system, I1 plus I2 plus I3. You have, this is I1, this is I2, this is I3. Solve this and send the solutions right now in the WhatsApp group. Right now, not after the classes, right now. So that your confidence and concept will build up. Right? Now the concept is continuous mass distribution. Continuous mass distribution. It's not the point mass. What already we have discussed about the continuous. For example, you take a rod of length L. It's called the continuous mass distribution because so many point masses are involved in this. This is a continuous mass distribution. So many point masses are involved here. For example, let's take the concept called moment of inertia of a rod. And before moving to that, in continuous mass distribution, one and only formula if you want to find the moment of inertia of the system. Remember, I is equal to integral x square into dm. There is a derivation for this, it's not required. Moment of inertia of a continuous mass distribution, one and only formula, integral x square into dm. Most of the students will keep dx here because you know integrations very well. Integral x square into dx andre x cube by 3. But it's not dx, it's dm. Integral x square into dm. Integral x square into dm. Once again I am telling you, do not get confused here, my dear children. Integral x square into dm. That's not dx. This is the one and only formula by which you can solve the maximum concepts called a moment of inertia of a continuous mass distribution. Get ready now. Moment of inertia of the rod. Rod. Imagine the situation. This is the rod I have now. Now, what is the case we are taking? You know, the rod length is L. Listen. The length of the rod is L. And what is dm, what is x, everything I'll tell you. Don't worry. This is the rod of length L from here. Observe. Right? Andre, this is the axis of rotation. X is equal to 0 point here. And this is what the point x is equal to L. Andre, the rod is having some limits in case of its length. So 0 to L is the limits. Keep it aside. Total mass of the rod is m. Total mass of the rod is m. All right. When the total mass is m, the length is L. At a distance x from the axis of rotation, at a distance x, some arbitrary point x, a small mass element is considered dm. Small mass element. Because I have told you already, this is the continuous mass distribution. There is dm here, there is dm, there is dm, there is dm, there is dm, there is dm here. At an arbitrary point, somewhere, a random point, at a distance x from the axis of rotation, a small mass element dm and the small length element dx is considered. This part, for your better understanding, this part. Small mass element, small length element. Like that, several mass elements are there. All those small mass elements, if you integrate, you get m. Several dx elements will be there. All these dx elements, if you combine, and if you add, and if you integrate, you get this L, length of the rod. Simple. Right. For the total mass, length is L. For the small mass element, length is dx. See? The one and only formula for continuous mass distribution identifying the moment of inertia is this one. I is equal to integral x square dm. From this, dm is equal to m by L into dx. Observe carefully. dm is equal to m by L into dx. Now, the moment of inertia is of the rod about this axis of rotation. Now, the axis of rotation is at the end of the rod. Look at here. Axis of rotation is about its end. Very, very important. Because this rod can rotate like this. Axis of rotation is at the end. It can rotate like this. And the same rod can also rotate like this. Axis of rotation is at the center of mass. See here. And the same rod can also be rotated like this, about this axis of rotation. I told you about the axis of rotation is changing and your moment of inertia will change. Right? So that's why it's most important. Moment of inertia of the rod. About what axis of rotation? How important? Fine. So I is equal to integral x square into dm. So integral x square into dm andre, see here. m by L into dx. So I is equal to E m by L will come out because it's constant. Mass of the rod, total mass m. Total length is L. Integral x square dx. Now you see, we are doing the integration with respect to dx. Andre, this x is having some limits, right? So 0 to L. So idu m by L integral x square andre x cube by 3 and the limits are 0 to L. So once again, m by L into L cube by 3, the limits substitute ಮಾಡಿದ್ರೆ sir ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ಹೆಂಗೆ sir ಅಂದ್ರೆ go back to your classes and listen to integration videos or look at the integration applications wherever it has come. Refer the notes. So limits, if you apply, you get L cube by 3 here. So this is 1 L and cancels, and ml square you get it. And moment of inertia, you know, ml square by 3. What is that? Moment of inertia of the rod about an axis passing through the end. So either rod. So this is what the end of the rod. Now the axis of rotation is the pen here. About this axis of rotation, so the rod is rotating. E case alli, this is the moment of inertia. E case alli, this is the moment of inertia. Alright? Alright everybody. Now the interesting thing I'll show you. So this is the center of mass of the rod. About the center of mass of the rod, so this is the moment of inertia, you know. So the moment of inertia of the rod about the center of mass, it is ml square by 12. What is that? ml square by 12. Look at here. So this is what the moment of inertia of the rod about its center of mass axis. So this is ml square by 12, and this we can prove. This we can prove. So by using a theorem called, there is a theorem here. Very important theorem is here. By using a theorem called parallel axis theorem. What's the theorem here? Parallel axis theorem. It's so simple, my dear students. The rod uncoiled. This is the axis passing through center of mass. And this is what another axis passing through at another end. This is moment of inertia of the rod about this axis is I. Moment of inertia of the rod about center of mass axis is ICM. There is a perpendicular distance between these two axes. This is one axis, this is another axis. So imagine that perpendicular distance is D. You know, parallel axis theorem tells that I is equal to ICM plus MD square. Observe everybody. Moment of inertia of the rod about any axis of rotation. Carefully observe. Not only here. This axis may be here. This axis may be here. This axis may be the other end. Moment of inertia of any moment of inertia of a rod about any axis of rotation we can find by using this formula. What is that? I. Moment of inertia of the rod about any axis of rotation. ICM. Moment of inertia of the rod about center of mass axis. Idu. Plus mass of the rod into D square. What is D? Perpendicular distance between center of mass axis and any other axis. md square. Moment of inertia of the rod about any axis of rotation, which is equal to moment of inertia of the rod about center of mass axis plus mass of the rod into square of the distance between these two axes. That's called parallel axis theorem. And by using parallel axis theorem, we are going to find ml square by 12. ml square by 12. And let's see, this is the application here. Let us check. This is the application, my dear students. This is the rod. This is the rod of length L. So this we know, a rod of length L. Observe carefully. What we have found about this axis of rotation, I, what is that I value? ml square by 3 anta we have got. This one only we got, right? ml square by 3. What we need? We need about the center of mass. What is the moment of inertia of this rod? Total rod length is L, right? Now this is perpendicular distance between these two rods. So D is equal to L by 2. From the parallel axis theorem, I is equal to ICM plus MD square. Let's substitute everything. I you know ml square by 3 and ICM, that's we are going to find. M, mass of the rod M, and D, what is D here? Perpendicular distance between two parallel axes. L by 2. Let's substitute. ml square by 3 is equal to ICM plus M L by 2 whole square. Now, ICM is equal to ml square by 3 minus ml square by 4. ml square by 3 minus ml square by 4 is how much? Is it ml square by 12, my dear students? Is it ml square by 12, my dear students? So that's a ICM. Moment of inertia of the rod about the center of mass axis is ml square by 12. Moment of inertia of the rod about the axis of rotation is at the end, it's ml square by 3. Remember, for example, if you go to the second PUC, there is a chapter called magnetism. There one magnet is kept. This magnet is rotating about the center of mass antara. ಆ ಕೇಸಲ್ಲಿ what's the moment of inertia? ml square by 12, because the magnet also can be considered as a uniform rod. Like this, connection will be there to the second PUC topics. About axis of rotation, the value is changing. When this is the axis of rotation, the value of moment of inertia is different. When this is the axis of rotation, the value of moment of inertia is different. Hagagi, that's called a tensor quantity. The conclusion of this is a moment of inertia is a tensor quantity. Right? That's it. That's it. Just write the good notes and prepare well, and any doubts you're welcome to ask, right? So tomorrow we'll be solving the maximum kind of numericals related to moment of inertia, parallel axis theorem, and there is another theorem called a perpendicular axis theorem, and that also will be discussed in the next class, right? So bye bye and signing off, all the best.